Hello everyone, welcome to Qubit classes. In this video on matrices, we will see the elementary transformations on those matrices, how to perform them, what are various types, and we will see an important concept in the matrix theory, which is the inverse of a matrix. So the concepts which we will cover in this video are what are row transformations and what are various types of row transformations. Similarly, column transformations and their types. Then we will see what is an inverse of a matrix. And finally, we will see what are the conditions or the necessities for existence of an inverse. We will learn these concepts by solving problems. So the first question is, perform the following row transformations on matrix A in given order. The first transformation is R12. Then, having done R12, we will be doing -2 into R3. And having performed these operations in the given order, we will perform the third operation, which is R1 plus 2R3. And this is matrix A. The first row is 1 2 1, the second row is 3 1 3, and the third row is -1 2 and -3. Now, the first transformation, which reads R12, means interchanging of row 1 and row 2. So, the original matrix had 1 2 1 as its first row and 3 1 3 as its second row. And on performing this operation R12, the second row will become the first row of the new matrix, highlighted in green color, and the first row, which is 1 2 1, will now become the second row. So an operation of this form R12 corresponds to interchanging rows 1 and 2. Now the next operation is -2 into R3. Note that we are performing this -2 into R3 on this new matrix. So -2 into R3 means multiplying each and every element of R3 with -2. So -2 into -1 will become 2. -2 into 2 will become -4. And -2 into -3 will become 6. So a transformation of this kind will give us an entire row multiplied by this number. In this case it is -2. Now the third transformation is R1 plus 2R3. Okay. Now the R1 in this matrix is 3 1 3 and R3 in this matrix is 2 -4 and 6. So this operation means we will take an element in R1, consider the first element, which is 3, and to this element we will add 2 into the corresponding element in the third row. So the first element in the third row is 2. So the first element in the first row of the new matrix will be 3 plus 2 into 2. Note that 3 is the first element of this matrix, 2 is the second element, 2 is the first element in the third row. Hence, R1 plus 2 R3 will give us 3 plus 2 into 2, which is 7. Similarly, consider the second element in first row and second element in the third row. On performing R1 plus 2 R3, this will give us 1 plus 2 into -4. So this will give us -7. And for this third element, we will be doing 3 plus 2 into 6, which is 3 plus 12, that is 15. So in this operation R1 plus 2 R3, We have taken an element in the first row and to that element we have multiplied the corresponding element in the third row but with this 2 as an additional multiple. So r1 plus 2r3 will give us 3 plus 2 into 2, 1 plus 2 into minus 4 and 3 plus 2 into minus 6 as the new first row. Therefore, we have successfully performed these three operations in the given order and we have obtained this matrix 7 minus 7 15 1 2 1 2 minus 4 6. Now, all these operations have not changed the order of the matrix. Originally it was 3 by 3 and the final matrix is also 3 by 3. Hence any row transformation does not change the order. This is an important point to be made here. We'll move on to next problem now. Perform the following column transformations on matrix A in given order. C2 3, C1 minus C2 and the third operation is 1 upon 2 into C2. The matrix A is 3 minus 1 2, 1 2 3 and 4 1 4. Now as we did for the first row transformation which was R12 where we interchange first and second rows. In this case C23 will give us the second and third columns interchanged. So the second column in the original matrix is minus 1 2 4 and the third column is 2 3 and 4. Now on performing this operation C23, the third column in the original matrix will become the second column in this new transformed matrix which is highlighted in the green color, and the second column in the original matrix A which was minus 1 2 1 will now become the third column which is minus 1 2 1 and this has been highlighted in yellow color. Now we will perform this second operation on this new matrix which is C1 minus C2. Now C1 minus C2 means we will take an element in the first column and we will subtract the corresponding element in the second column from the first element. So C1 minus C2 will give us 3 minus 2, 1 minus 3 and 4 minus 4. The other two columns will remain unaltered. So 3 minus 2 give us 1, 1 minus 3 will be minus 2 and 4 minus 4 will be 0. Now the next operation is, or the transformation is 1 upon 2 into C2. So now we will take each and every element of C2 of this new matrix which is 2, 3 and 4, the second column, and we will multiply each and every element by 1 upon 2. So the first element will be 2 by 2 which is 1, the second element will be 3 by 2 which is 1.5 and the third element will be 4 by 2 which is 2. So we have successfully performed these transformations C23, C1 minus C2 and 1 upon 2 C2 on this matrix A. As we saw for row transformations, the column transformations will not change the order. So originally it was 3 by 3 and the order of this final matrix is also 3 by 3. And the notations which we have used to denote the transformations are similar to the notation which we were using for row transformations. So if you have R here, that will mean a row transformation. If we have a C here, it will mean a column transformation. Now we'll move on to the third problem. Define the inverse of a matrix and also state the conditions for existence of the inverse. Now, if you have seen our previous video, we have stated there that Finding an inverse of a matrix is an operation which is similar to division of numbers. So in matrix theory, the division of two matrices is not defined, but we have an operation similar to the division which is known as finding an inverse of a matrix. Now we will see its definition. Let A be a square matrix. If there exists a matrix B such that A into B is equal to B into A is equal to I, then B is called an inverse of A. Now I is an identity matrix. Identity matrix is a square matrix whose elements are equal to 0 except the diagonal elements, and the diagonal elements are equal to 1. So B is such a matrix which when multiplied with A will give us an identity matrix. So we write B as A raised to minus 1 and we read it as B is equal to A inverse. Okay, now we will see the properties of the inverse. A inverse exists if and only if determinant of A is not equal to 0. So this statement implies that only square matrices have inverse. If the number of rows in a matrix and number of columns in a matrix are unequal, then the matrix will not have an inverse because it won't be a square matrix. Now given that the matrix is a square one, A inverse will exist only if the determinant of that matrix is not equal to 0. And the next property is, this is also very important, if A inverse exists, then it is unique. This means, suppose you know a matrix B, which when multiplied with A, you will get, you are getting I. This implies that there will not be any other matrix C such that A into C equal to C into A equal to I. And if you find such a matrix C, it will always be equal to B. Thus, the inverse of any matrix is always unique. Okay, so we already explained this. So I is an identity matrix. It is a square matrix such that Aij is equal to 1. Aij means the element of the matrix which is present in the ith row and jth column. So when the row number and column number are equal, that element should be 1, and if the row number and column number are unequal, then the number should be 0. This is how we define identity matrix. So to define an inverse, we must know what an identity matrix is. So the product of any matrix A and its inverse is I. Okay. Now let us see an example. Consider matrix A, which is a 2 by 2 matrix. The first row is 3, 5 and the second row is 1, 2. Now we will find the determinant of A, which will be 3 into 2 minus 5 into 1, which is 6 minus 5, which is 1, which is not equal to 0. Okay, so we have verified that the A inverse will exist because the determinant is not equal to 0. Okay, now consider this matrix B, which is 2 minus 5 minus 1 and 3. This is also a 2 by 2 matrix. And we will check whether B is an inverse of A. So we will multiply B and B with A. Now in the previous video we have defined or we have stated how to multiply two matrices. So we will take the first row and first column and we will multiply respective elements and add them. So it will be 3 into 2 plus 5 into minus 1. Then 3 into minus, oh sorry, there should be 3 into minus 5 plus 5 into 3. The third one will be 1 into 2 plus 2 into minus 1. And the fourth one will be 1 into minus 5 plus 2 into 3. So 6 minus 5 will give us 1. my so this is minus 15, sorry. So minus 15 plus 15 will give us 0. This 2 and this minus 2 will be 0. And this minus 5 plus 6 gives us 1. So this is an identity matrix. Okay. So A into B is giving us an identity matrix. Hence, we can call B as the inverse of A. Hence, B is A inverse. Now, it can also be shown that if B is an inverse of A, then A is the inverse of B. Okay. So in this video, we studied the following things. First, we solved a problem on row transformations, where we did these operations, interchanging two rows. So if it is R12, then we will interchange the first row and the second row. Then multiplying an entire row by a number, let's say 2 by 3 into R4. So by this, we mean taking each and every element of R4 and multiplying it with this number 2 by 3. And the third operation is a combination of these two operations, which is R2 minus 3R4. In this operation, we will take an element in R2, we'll take the corresponding element in R4, and we will perform this operation. We will subtract this product 3 into the corresponding element in R4 from the corresponding element in the second row. We also saw the column transformations, where we basically perform operations on one or more columns. These include interchanging two columns, multiplying an entire column by a number, and a combination of these two transformations. We also saw what is an inverse of a matrix. So if A inverse is the inverse of matrix A into A inverse will be I. Now, we stated that finding an inverse of a matrix is an operation which is similar to division. And this is how it goes. Consider the number 2. Okay. Now we know that 2 into 1 upon 2 is equal to 1. So 1 upon 2 in the language of indices can be written as 2 raised to minus 1. So 2 into 2 raised to minus 1 is 1, and A into A raised to minus 1 is I. But note that when we perform the operation of inverse on any matrix, we can't take this A inverse in the denominator of this I, because division of matrices are different. But if we have the number 2, we can write it as 2 into 1 upon 2 is equal to 1, and we can take this 1 upon 2 on the right hand side, but that operation is not allowed in the for matrices. So this is the similarity between the division of any two numbers and I should say finding a reciprocal of any number and the inverse. And we also saw the condition for existence of an inverse. So if only square matrices have an inverse, and if the determinant of that square matrix is not equal to 0, only then the inverse will exist. Okay. So although we saw an example where we multiplied a matrix with another matrix and we somehow got the identity matrix, but we have not said anything about how to find that second matrix which will actually give us the identity matrix. So in the next video, we will see the methods to find inverse of a matrix. Okay. So I hope you understood this video, the transformations part and the inverse part. So we thank you for watching, and if you have any queries, you can contact us on qubitclasses@gmail.com. And don't forget to subscribe to our YouTube channel. Thank you.